Welcome to the Infosys Science Foundation lecture. I'm honored to introduce our speaker today, Professor Shafi Goldwasser. Shafi is the director of the Weizmann Institute for the Theory of Computing and is a professor at UC Berkeley, MIT, and the Weizmann Institute. She holds a BS in Applied Mathematics from CMU and MS and PhD in Computer Science from UC Berkeley. For the theoretical computer scientists in the audience, especially cryptographers, Shafi needs no introduction. She is the co-inventor of probabilistic encryption, which is the gold standard for secure encryption today, the co-inventor of zero-knowledge proofs that is rapidly making its way from theory to impactful practice. Her contributions include elliptic curve primality tests, hardness of approximation, combinatorial property testing, and the list goes on. It is impossible to overstate how much impact Shafi has had in shaping the field of cryptography as we know it today. She is a recipient of the ACM Turing Award, 2 Gödel Prizes, ACM Hopper Award, RSA Award in Mathematics, ACM Franklin Medal, Simon Foundation Investigator Award, and L'Oreal UNESCO Women in Science Award. Shafi is a member of the NAS, NAE, AAAS, Russian and Israeli Academies of Science, and London Royal Mathematical Society. She also holds honorary degrees from many universities. There are many people who are good researchers, excellent educators, and visionary scientists, but Shafi is someone who encompasses all of these and a source of inspiration to many in the field. Shafi, we are thrilled to have you here. Over to you.
Thank you very much. So can you hear me? Yeah. Okay, thank you very much for the invitation, and it's a very generous introduction. So what I'll speak about today is, the title of my talk is The Right to Deny. What do I mean by that? So first, we'll get to the right to deny in like a slide or two, but I want to point out that a lot of people are, and including myself, have been paying attention these days to these questions that are in the realm of what's called safe machine learning. And when you say safe machine learning, you mean many things, but usually you mean one of these 4 things, which is privacy in machine learning models, which use data, so you want to maintain the privacy of the data, verification maybe of the machine learning model properties, robustness to unforeseen input distributions, or people know this under the name of adversarial machine learning. Algorithmic fairness has become a very big topic, and there's a lot of research in this. But all of this research essentially concedes that the concentration of power is in the hands of those who have the data, and you are hoping that they're going to utilize some of these methods, either that they will learn on method employing the privacy techniques that you have developed, that they will make sure their algorithms are robust to the extent possible, that they'll make sure the algorithms are fair, and so forth. So you're developing these methods, and you're hoping that the people who are actually writing the machine learning code are going to use the methods you've developed. Maybe verification is a bit of an exception, because you could verify maybe not being the one who developed the model, properties of the model, okay? And what this talk about essentially it says is, okay, if we're assuming that these centers who have all the data and all the power are benevolent, that's a bit risky, because maybe they're not. Or maybe they're going to be taken over by someone who is not so benevolent, and all this concentration of power in one place has some risks to it. So I guess it's a quote here, so living in a surveillance state will not be made much better if the cameras watching you aren't discriminating against you. So a lot of people talking about cameras are discriminating, and it's an important issue. But the fact that there are cameras everywhere and they're recording everything you do all the time, that's maybe, you know, even a larger issue, or at least as important. And it brings me to the topic of my talk, I hope. Right. So essentially around 1890, there was this paper written by someone who then later became Judge Brandeis and a colleague of his in a law firm. And they wrote, this is a very famous paper, people have probably seen it, at least something quoted from it, which is this phrase called the right to be left alone. So in this paper they use this phrase, the right to be left alone, saying, and I think it was right on the heels of this idea that cameras were not, you didn't have to go to a camera shop to be photographed, but people could carry cameras and take pictures of you in the street. It's like, how could this happen? You know, How about my right to be left alone? Now, it's laughable, really, if we think about what we do today, right? You know everything about me. Every time I go to a service, you know, people are collecting information about me. And still, you know, it's a very interesting phrase, and a lot of the work that we do in fields of cryptography is trying to say that we still have some right to be left alone. Maybe our communications are private, maybe our use of the cloud, we'd like to make it private and so forth. But I guess what I'm saying is that the topic of my talk today is going to be deniability. So I'd like to propose that that might be the ultimate extension of the right to be left alone. So the right to be left alone in our world is very difficult. You know, so suppose I don't have the compute, I don't do the things I want to do, so I go to the cloud. And then there it is, you know, my data is out there, and even if it's encrypted, there's some trace of it, okay, and the trace of the computations that I've done. So in what sense am I going to be left alone if somebody later wants to pursue and say, give me all your emails, give me all your computations? We are saying that today that we want to talk about tools which allow you to deny. Say, no, this is not what I said, this is not what I computed. Even though you have some public record of what I've done, you have a way to formally deny what you have done. And perhaps this expands in a good way on the idea of the right to be left alone. So I'm not exactly left alone, but since I can deny everything and have some record of, I can sort of prove that I deny properly, it would mean that I can't be taken to court or I can't be prosecuted because I've denied it and I have a legitimate course of denying. This will become more clear as I go along. Let me give you a motivation which is more concrete, okay? And where this whole idea of deniability came up many years ago in cryptography. So many years ago, I think it was Ron Rivest at MIT. He was teaching a course on cryptography, and he was interested in electronic voting. At the time, very naive, you know, like why can't we just vote at home? If you're trying to encourage a lot of people to vote, put your vote, encrypt it, send it to the government. Then there was a student there, Josh Benelo, and he came up with this nice homomorphic encryption method, which was additive, which means you can individuals encrypt their votes, and then there's a way to figure out from all these encrypted votes what the encrypted sum of the votes is, and then you just decrypt that sum, and now you know if you voted more for, let's say if there are two parties, it's closer to 0, closer to 1, okay? The understanding was that in order to have a good electronic voting system, you need the right for equal and effective access to a polling station. Check, just send your encrypted voted online. You need the right to vote in secret. You vote at home, and you encrypt your vote, so that's secret. You need the right for a vote to be awarded equivalent weight. Yes, because this way of tallying was such that they didn't give one vote 5 votes, but every single vote counted once. But there is one more thing in voting. So this is just a schematic. So let's say vote for 0, vote for 1. There's the government. Let's say they publish on the election day some public key, and they keep secret some secret key. And then all these individuals, they compute a ciphertext, CT, which is the encryption of their individual votes, encrypt of 0, encrypt of 1, vote for 0, vote for 1. And then there is a way using this homomorphic encryption thing to compute a new ciphertext, CT star, which is essentially using just these individual votes, encrypted votes, and then tallies them. Magically, it comes up with this ciphertext so that when you decrypt that special ciphertext, you get the sum of the votes and not individual votes. So of course you could ask is, wait a second, if the government has the secret key, who's to say that they're not going to also encrypt individual votes and only going to decrypt individual votes, but only decrypt a tally? And the answer to that is usually that there isn't really a safe with a secret key in it that the government can open, but this safe, there's a split secret key, so secret shared, and shares of the secret key are in different safes, and only if all these safes come together, you can decrypt, and they will, and not everybody who holds the shares is bad, and therefore, if not everybody's bad, then one of the shares won't come together when you're trying to decrypt individual votes, and you're only going to decrypt a tally. Okay. So this is wonderful. It looks like the problem is solved. The one problem is that one more requirement for voting is that you shouldn't be able to buy somebody's vote, okay? So when we go into the polling station, we close the screen behind us, we are assuming there are no cameras there to see who I voted for. And however, what about when you vote online like this? So people cannot see what you voted for, but they can see the encryption of what you voted for, okay? So does that make it more possible to buy votes, okay? And the observation was already at the time was that yes, unfortunately you can buy votes as follows. This person says, hey Bob, who'd you vote for? And prove that you voted for me, and if you prove it, we're gonna give you money, say. So how do I prove for an electrical for electronic voting, then he gets money, that I voted for Bob? I show him exactly what I did. I said, listen, I encrypted a vote for you. Now, encryption is usually randomized, so I give the randomness. I give the randomness, I give the vote, and they can redo my operation and see that that's really what I sent the government. And then Bob's happy, gives you money. He bought your vote, or gives you love. By the way, these slides, I have 3 different results I'm going to talk about, and they're all slides that I've changed by my co-authors. So there will be 3 different styles, and I will give references, credits when the time comes. But in any case, you understand the problem? So if I voted electronically and everybody can see this encrypted vote, now they can come to me and say, hey, who'd you vote for? And I can prove to them who I voted for. And therefore, this is an incentive to vote for one versus the other, which is not supposed to exist. The reason going behind a curtain is a good idea is because then I can really vote for one person, claim I voted for another person. It doesn't really shouldn't change my vote. Of course, if the whole country votes for one person and I claim I voted for another one, that's one way to check. But you understand the point. Okay, so this was a problem in the solution that Benello gave. And in '97, there was this beautiful, beautiful paper by Ran Canetti, Moni Naor, Cynthia Dwork, Raphael Ostrovsky. They had this notion, okay? They said, you know what? We're going to come up with a new kind of encryption scheme, which is called deniable encryption scheme. And the idea of a deniable encryption scheme is that you could vote, let's say, for somebody. This is the real vote, okay? And when you send the ciphertext to the government, you know, to tally. But when this guy comes around and say, hey, Bob, prove that you voted for me, in this encryption scheme, you could actually prove to him you voted yes or you voted no. So you can both prove that you actually encrypted this vote, but you can also prove that you encrypted the complement vote. Now, what does it mean, prove? To prove, you have to show who you voted for, and so the randomness, so that when you encrypt it using that randomness in that vote, that's the ciphertext that was sent. So somehow they showed a way that there's a faking routine that produces an alternative randomness that with this randomness and the complement vote, the same ciphertext would have been sent. Okay, so the ciphertext is, when you encrypt under the true vote in R, is going to be exactly the same as the complement vote in R prime. Seems very bizarre, okay? So what's inherent about this idea is that there is a small probability of error when you decrypt. So there is some small, negligibly, exponentially small probability the government will, instead of understanding your vote correctly, will understand incorrectly. But you can make that probability extremely small, okay? So overall, the government will understand all the votes correctly and tally them correctly. But this small probability of error enables this mechanism so that for every vote that I send, I can actually produce randomness that proves that I voted the complement vote. Bizarre. So I, in some sense, can prove that I voted for, what was the last election in the US? I can prove that I voted for Trump, and I can prove that I voted for Biden, and it looks the same. What does it mean looks the same? Well, there's some randomness. There's the fake randomness, and there's the real randomness. So this is the fake distribution. That's when I vote using fake randomness that was produced by the fake routine, and this is when I voted using the real randomness. And these randomness should be equally, it shouldn't be able to tell them apart. They should look the same. So whoever that agent was that was trying to buy my votes really can't tell whether I'm telling him the truth or I'm just claiming something that I didn't do. Really an ingenious idea. So clever, so beautiful. Somebody asked me, what is exciting about cryptography? Well, every once in a while there's a new idea. That's an exciting idea. Okay, so they did this, they had this notion, they had a solution. They also had some minuses about their solution. So what is a minus? One of them is that you really want this indistinguishable. You want this guy to believe both when you tell the truth and when you fake him out. So he shouldn't be able to distinguish these distributions at all. So this distinguishing between real R and fake R prime, okay, the probability of distinguishing should be very low. Any questions? Because I know there are people here who don't work on this kind of stuff at all. And yes? What?
So you're saying that it works for complement, like you have, like, they're like a binary system, like either 0 or 1. So what if you have more than one option?
Oh, you could do, yeah, you could do arbitrary, you could do larger message space. You could vote for 10 things for.
Okay, and
yeah.
then also it will, so in that case.
And then in that case, the way you want to say that for every pair of values in the value set that you can vote for, you could switch from one to the other.
Oh, okay.
Okay, so you have 10 candidates, you can switch from candidate A to candidate L, you know, or whatever. So 1 to 7, 3 to 5, and so forth, okay? Yeah. Very small, because individual encryptions have some probability of being decrypted incorrectly, but exponentially small. And the number of votes is polynomial. In our world, always there's polynomial versus exponential. So if there's exponentially small probability of making a mistake, overall, you're really never going to make a mistake. So the loss in vote, yeah.
The second question is related to now that you can prove either way. Is the idea that it's a useless exercise for people to buy the vote?
Exactly. That's exactly the idea. Is yes, you can try to coerce me, but there's no point in it, so don't. I mean, you can try, but it's a futile exercise. Exactly. Yes?
Now I understand the motivation for deniability and so on, but it can also be used in a malicious way. We did something wrong in the past.
I completely agree. That's not. Okay, so you have to, for at least an hour, suspend this worry and say what we want to do is deny. Now, you say we deny, but everybody else is talking about fake news. Now you can also deny that it's fake. So to answer that, you say, let's have another key, a trapdoor, that is in extreme circumstances, they can overrule your denying. However, you know, it's this fight, it's this pendulum, right, between enforcing the law and not being prosecuted by, you know, an authority. I agree with you. I'm talking about how to deny. If you like, we can just think about it as intellectually interesting. I think if you can get both and put some mechanisms on when you can deny and when you can not deny, it would be more interesting. Okay, great question. So and it seems paradoxical almost, but it's not. So the government has the secret key. And if you have the secret key, you can figure out that when you decrypt, you're going to get the right vote. It's just that when that strange person with the hat comes to me, the sender, I can claim that I did one or the other. But the other side that has the secret key, they can tally the votes up correctly. Yes? Our government? No.
The distribution is the same, right?
Yeah.
So I voted for some, say it's a binary thing, I voted 1. Now the government has to decrypt it. Can it decrypt it to 0? Since there is a randomness which is...
Okay, so you could add the government having a zero-knowledge proof system or something where they prove that they have decrypted correctly. Namely, they use their secret key correctly, and that will not divulge the votes, but will only divulge the outcome, but prove that they did not do something funny.
Okay.
But you solve that by another problem.
I see. Thank you.
Yes, yes, yes. It's a scheme where they give you an efficient subroutine for faking. Otherwise, it's useless. Okay. So with all this, what was the assumption? So you know, in cryptography, often you don't get something for nothing. There's usually some computational assumption, but the assumption in this original paper was really beautiful, simple assumption, and that is that this primitive called trapdoor functions exists. It's just that there are functions which are easy to compute, hard to invert unless you know some trapdoor. Okay. And we can base this on factoring, on hardness of lattice problems, on bilinear maps, on all kinds of hard computational problems in mathematics. And And they showed a construction. The minus was that in order to make this, a beautiful thing where they are and the R prime really are indistinguishable from each other, like they look very close, the size of the ciphertext in their solution grew in the inverse of the difference probability. So if you wanted it to be like 1 in n is some sort of security parameter here, then the ciphertext would be linear. But if that's not a very big probability of detection, you could detect, in linear time. But if you wanted to make it 1 in 2 to the n, okay, so they can't tell apart in exponential time whether you voted for R or R prime, then the size of the ciphertext would be 2 to the n, too large. Okay, so there was a minus in their solution. And in fact, there was some sort of big question, all right, can you get deniability versus compactness? That was open problem. There's another, I want to say something. You ask very good questions, but you didn't ask the obvious question. The obvious question is, if you want to do this, why do you need all this sophisticated mathematics? Why don't you just erase your randomness? So I vote, I erase, then somebody says, hey, showed me that you voted for me. And I say, well, I erased it. Well, because I want money. I don't care about the election. So I would like to vote for you, and I'd like to convince you that I voted for you. So erasing doesn't answer that. And two, I mean, I don't know if I want money, but whoever it is, Bob there, wants money. And furthermore, maybe by regulation, you're not supposed to erase your randomness. So erase, plus it's a very simple solution. And the whole beautiful intellectual fun doesn't come up here. So erasing is not not a legitimate solution. Okay, so long history followed. People got very fascinated in the way the cryptographers do, and they talked about receiver deniability, and that is that the government, let's say somebody got a message from me, and I have the secret key, and then the government says, hey, show me all the messages you received, give me the secret key. I might want to deny that. Can I come up with an alternative secret key that doesn't really decrypt the messages properly, but decrypts them in such a way that some messages are flipped? So people defined that, then they showed some lower bounds on that. They talked about byte deniability. There's all kinds of lower bounds that are showed here about key sizes, ciphertext sizes, and so forth. Okay, lots of work. Significant step forward was in 2014. This result by Amit Sahai and Brent Waters, where they showed this result that some of the cryptographers here know that there's something called I/O obfuscation, some way of program obfuscation, where they showed that if you have such program obfuscation, then you could do deniability, achieving both compactness and deniability and everything else you want. Problem is that this I/O obfuscation is a very heavy tool, heavy hammer. At the time, it was just a conjectured thing. They had some sort of a blueprint of how to get it. These days, there are already concrete assumptions that if you could put all of them together and you believe them, you could build such I/O. But in terms of deniable encryption, the problem really is that if you look at from 1997 to when that breakthrough, in cryptography, people love to do wonderful things, okay? And in the beginning, we say we assume anything. Let's assume factoring is hard, and lattices are hard, and I don't know, and adding and dividing is hard. That's a joke. But we are willing to throw, because it's not hard, we're willing to put as many assumptions as we like. But the truth is, at the end, the value of the result is related to the value of the assumption. So it's beautiful that we have ideas, but at the end, if the assumptions are false, then the security doesn't hold. So there is a big difference between the assumptions they made in 97 with that simple trapdoor function, which can be based on any kind of polynomial, any kind of hard problem in some sense that we have in cryptography, versus what Sahai and Waters assume, where they assume that specific problems are hard and they're exponentially hard, so they're extremely hard, okay? So the open question that remained here is, how can you get reasonable assumptions, compactness, and deniability? And finally, as is always the case with researchers, because we kind of get fixated, this is the problem, is like we got this deniable system is no longer homomorphic. So in terms of applying to encryption, in a voting doesn't work. So you could have deniable encryption, but you can't add these encryptions and then tally up the votes and then deny that you sold your vote. Okay, so remember, to do the elections, we needed to have homomorphic. We needed to be able to tally up votes without decrypting individually. And we wanted deniability so that votes cannot be bought. OK, so this brings me to what we're going to do today. There are going to be 3 parts, although I think that with the questions, probably going to be 2 parts. And part 1 is joint work with Shweta Agarwal, who I think is a professor in Chennai, and Salit Mossa, a graduate student of mine that now works in Algorand. And what we show is a fully homomorphic encryption scheme, so not just some homomorphism, but fully homomorphic encryption scheme, which has more applications than just elections, which I'll mention in a minute, which is also deniable. And we do this in a way where the ciphertexts are compact. It has some other issues, but and the assumption is sort of a reasonable assumption is learning with errors. It's hard. We know right now it's hard also for quantum computation. This is a mouthful. I'll repeat it. That will be part one. Part two is more recent work with Umesh Bazirani and Andrea D'Angelo at Berkeley. And is the paper here? No, I think, oh, sorry. I think when I go to part two, I'll post write the reference to the paper. And what we do is we say, you know what, suppose quantum computers are going to be a reality. Is there something that quantum quantum power allows to do in the realm of deniability that classically is impossible? So there are certain things which are classically impossible, like having a zero decryption error. And it turns out, or like coercing after the fact. So in this whole story, the coercer comes afterwards and say, hey, prove you vote, and I give him the vote and the randomness. But if he told me before, 5 days before, this is the randomness you should use, and then he just checks that I use the right randomness, then he can coerce me before the fact, right? And in fact, classically, you can prove that you can't avoid that. Before the fact, you can always coerce people. If you tie their hands, you tell them exactly what to do, in some sense, you look over their shoulder that they did exactly this, there's nothing to do. It turns out that if you let use quantum power to a fairly limited sense, you are able to come up with a secure, with a way to vote, okay, which is deniable in a much stronger sense. Like you cannot coerce even before the fact. You have a zero decryption error. So there's some things about quantum computation, some about the magic of quantum enables you to do things we cannot do classically. And somebody asked me today, I think we had a fire chat, and they asked me, or maybe it was with the students meeting, I already forget. But somebody asked me, what are we going to do when quantum is there? It's going to, all this cryptography that you've developed is worth nothing. And I believe it's quite the opposite, that we can replace the cryptography we've already developed by, let us say, lattice-based cryptography, which we don't know how to break on quantum. And if lattice will break, we'll find something else. But there is some ability that quantum computers give you that they break some things we can't do classically, that in the event, which I don't know if it's going to happen or not, that there will be quantum computers available, we probably can do things we cannot do today. And they will be not in the direction of breaking, but they will be in the direction of giving some extra power that we didn't think was possible. Okay, and the last thing will be about receiver deniable, if we get to it. Okay, all right, so let's start with this first result, like deniable encryption in this story that I told you. So the sender wants to deny that he sent one message versus the other. But I want to have it also homomorphic encryption. So you must have seen several talks here about fully homomorphic encryption, but I will say what the essence is. So the essence, so fully homomorphic encryption is something that came up in 2008 by a paper of Craig Gentry. And then I think the scheme that most people use these days is one of these two. This is by Zvika Barkursky, Craig Gentry, and Vinod Vaikunthanathan from 2012. And this is, I think, Garge, Sahai, and Waters, 2013. These are encryption schemes, which are phenomenal in the following sense. They can do this. You know, you can sort of encrypt as a client data, send it to this encrypted data, even to a cloud. The cloud, you give it some ability to evaluate, it's called an evaluation key. The cloud now can run arbitrary programs, okay? Or usually we think of them as Boolean circuits on these encrypted data without decrypting it. So the cloud doesn't know how to decrypt. Later, they return to you the output of the computation, the result of running all these programs in an encrypted fashion. So they never decrypted. They just did this engine of programming. But you, the client, know how to decrypt. You can decrypt the result of the computation. So in a sense, it's moving all the computational, even if all the computational power is in the cloud, you can be safe and just send your data encrypted to the cloud. It does the computation, and then it gives you back the result, which you can decrypt. Okay, beautiful. Now, it's expressive, so you could supports arbitrary circuits. You know, it's compact. Okay, so you send an encryption of the inputs, and you get encryption of the outputs. You don't have to keep any intermediary result. Only the cloud has to keep it. It's based on learning with errors, which is a problem that I think is easier to comprehend than the lattice problems, but it's equivalent to it. So the hard problem here is not factoring integers, but just think that you have a system of equations, modular equations. The unknowns are these s's, which you can think as numbers in between 1 and 17, or minus 17 and 17, okay? And this is a secret. And you don't have the real equations, because if you had the equations, you could do linear algebra and find what these s's are. You have sort of dirty equations. So these equations are really not correct. They're off by some error, okay? But you're given a system of equations, and the hard problem is to find the s's. This is called learning with errors. It's a hard problem, even we don't know how to solve it by quantum computers. And this is the current hard problem that the modern cryptographic systems that are being proposed, including fully homomorphic encryption, are based on. If this is a hard problem, to find S, then we can find public key cryptography, digital signatures, fully homomorphic encryption, and so forth. You look like you want to ask a question. No, okay, fine. Okay, so this is what homomorphic encryption allows you to do. And it's composed usually of a way to generate keys, a way to encrypt and decrypt, a way to encrypt, a way to decrypt, and a way to evaluate in the cloud. So there's a routine so that the cloud, he gets this evaluation key, yes, and then he can evaluate. Yes? The 4? Where is there 4? No. This is just an arbitrary. The not important. The 17 is not important. The 4 is because there's S1, S2, S3, S4.
But if I had 3 as well, it's fine.
For the hardness, yeah, I think it's fine. It's even 2 is fine. You know. Okay. So what's important actually is the 17 is the size of the field and the error. Yeah. And you can have also many equations. For this, brute force, when we talk about solutions, we talk about polynomial time. You could, yeah. So there is a brute force solution, because even if this problem seems to be difficult, even if the error is just +1, -1. So each one of them is either off by 1 or -1. So you would have to try all possibilities, you know, for, so here it matters the number of equations, the number of s's also, because you have to try all possibilities. That would be an exponential effort, and that's considered too much effort. So it's all asymptotics, right? The 4 is something that can grow. The 17 is something that can grow. Yeah. Yeah.
In case of voting, why do we need fully homomorphic encryption? Because
we just need additive, right?
But the government already knows the secret key. In that case.
No. That's the key. If the government knows the secret key, then we're in trouble, because then they could decrypt my vote and know what I voted for, your vote. No, it denies the privacy. So I think I said in the beginning there was the safe and the secret key was in there. We don't want to give the government the access to the safe. We want to split the secret key into shares. Let's say there's the government, there's the law, there's Congress, I don't know, whoever, the distribution of power, and they have to come together, and they only come together to decrypt the outcome. Good question. I said it, but too quick and too early. Okay? All right. So why, okay, maybe it's the next, yeah, before the theorem, I want to say, why do we need fully homomorphic encryption? Because, forget the election. I'm thinking cloud computing. I want to put all my data in the cloud, encrypted. I want the cloud to do the computations for me, and then I want to get the results. And I don't want to worry about the fact that tomorrow somebody's going to tell me, I want you to show me everything you encrypted, what it was, all the computations you've done. How am I going to do that? I want to be able to deny it. And if it's fully homomorphic, it means that for every computation I'm going to do, I can deny it. Now, you know, there are some subclasses of fully homomorphic where there's some things you can do and some things you cannot do. Maybe that's one answer to the question of what should you be able to deny everything, and say, no, you should only be able to deny some of the computations and not others. So if you can deny fully homomorphic encryption, you can also deny this cloud computing engine. Okay. So what does the theorem say? The theorem says we can construct a deniable fully homomorphic encryption scheme. The security will be based on the hardness of layering with errors, which is the problem that I showed you. The ciphertext will be compact. So the size now is going to be independent of the probability you can distinguish between R and R prime. Remember I said that the solutions were not compact. And we are going to distinguish between online and offline encryption time. Offline will be short, okay? But unfortunately, this is not the ultimate result. When we go to quantum, we will get, in some sense, the ultimate result. It's still going to be the case that during encryption time will be long. If I want to get, it will be essentially 1 over the probability of distinguish between R and R prime. So encryption time, the online encryption time will grow with how far apart R and R prime are. So if they're 1 over n apart, the encryption time will be linear. If they're 1 over 2 to the n, the encryption time will be exponential. So we haven't completely, we have gotten over compactness. We have this online, offline, good, beneficial idea, but we haven't completely solved the problem. However, we did get homomorphic encryption, and we did get a much lower assumption. No. So in the original paper on deniable, they had a lower bound, but it's not right. I mean, in the sense, you know, lower bounds, often you define it so you can prove a lower bound. And obviously, they proved that compactness is impossible, but it's not impossible because we can do it. Okay, so we did this. How do we do it? Now, I know that most of you are not cryptographers, but I don't know how to give a whole talk without some technical stuff, so I'll do something, okay? It's about 5 minutes. And I'll try to say it in a way that's accessible to most people. So usually when you put your mind to do a deniable system, all you care about is deniable. But we're not going to do it that way. We're going to take an existing homomorphic encryption scheme, maybe change a few of the properties, and add deniability to it. In fact, the way we're going to do it, do you hear me or something happened? No, you hear me. The way we're going to do it is use some of the properties which are, is it lower voice? Something happened. Hello? I think it's better. Yeah. So somehow we're going to take two schemes. We're going to take a homomorphic encryption scheme, and we're going to take a deniable encryption scheme, which just means that there's a fake subroutine, and we're combining them together. So the new system will also able to evaluate in the cloud and fake. So that is produce alternative randomness. Wonderful. So just a little bit to remember syntax. Evaluation means that there's sort of a public key which enables you to encrypt a whole bunch of ciphertext and some function, and it produces a new ciphertext CT star, so that when you decrypt it, you get the function F applied to the plain text. So you homomorphic, you somehow come up with a ciphertext who, when you decrypt it, is the result of running F on the plain text. Okay. And fake means that you can switch between B to B prime. For the sake of this talk, it will be between 0 and 1, but this results really can go from message to message prime, where there are arbitrary strings in some set of values. Okay, so I think the most interesting thing about this, I think fully homomorphic encryption is really, the way it's done is a genial idea, okay? And if people have heard it and don't remember, or never heard about it, if you get this out of this talk, you really got something, okay? It's a beautiful idea, and what I'll show you is that idea, in addition, can carry deniability with it, okay? So essentially, we need a special homomorphic encryption scheme. There's a whole bunch of properties here. Really, let's just focus on a few of them. One of them is that when you look at the ciphertext, okay, whether it's encrypting Shafi, encrypting Biden, encrypting Trump, we're all running for president, it looks like it's a random. The ciphertext looks like you can't distinguish random from pseudorandom, so they look pseudorandom, okay? And that's something you can get. Second of all, what we need for our thing to work is that there's at least this following homomorphic operation, and that is that if I'm given an encryption of A, say, an encryption of B, I'm able, this is just notation, to come up with a new ciphertext, CT star, which I'm going to donate like encryption of A with this strange operation. Let's think of it as an XOR, encryption of B, such that when you decrypt this new ciphertext, this notation for a new ciphertext, you will get essentially the sum mod 2 of what was encrypted of A and B. Okay, so there is a way to take two ciphertexts, one encrypting A and one encrypting B, and come up with a new ciphertext that encrypts A plus B mod 2. Okay, that's all I need to retain from this idea of homomorphic encryption. I'm able to come up with ciphertexts that when you decrypt them, it's the sum mod 2 of the respective plaintext. Okay, and there's two more properties, and that is that magically, but it's very easy to take existing homomorphic encryption and get this extra property. If I just put a random number in the space of where the ciphertext live, not really by encrypting, just picking a random something in the range, okay, or the codomain, then, and I run a decryption routine on it, it decrypts to 0. So if you think about this, really, you have the whole you have the space of where ciphertexts lie. There's sort of the legal zeros, which were obtained by encrypting a 0. There's the legal ones, which were obtained by encrypting a 1. And then there's all the stuff that never would have come up by legally encrypting. But still, if I took something from wasn't legally encryption of 0 or legal encryption of 1, and I tried to decrypt it, a random element in this whole space, it will decrypt to 0 with very high probability. Weird property will be useful. And then I need something which is called bootstrapping, which I will not get into right now. Okay? Yeah.
How large is the legal zeros and ones?
Small.
With respect to
Might be exponentially small. Okay? So there's a very large space, but really the number of legal encryptions, I mean, it's a large space, but within that, it's exponentially small. Okay. Okay. All right. So we have schemes that satisfy almost all these properties. And now comes the bootstrapping magic. So this is the thing that I think is magical about homomorphic encryption. So the idea of homomorphic encryption that Gentry already had was this. Here's what the idea was. And I remember I was in an Oberwolfach conference, and I had breakfast, and he said he could do this. And I said, really, how do you do it? And I didn't expect to understand anything. And he told me the idea over like 10 minutes of breakfast, okay, in a way that I could understand it. Because I think any time that you have a really big idea, you can explain it over breakfast in 10 minutes. Okay, so the idea there was this. How do you get homomorphic evaluation? How can you evaluate arbitrary programs unencrypted so that at the end you get the value, you get a ciphertext that decrypts the program running on the plain text? So the idea was that, first of all, every ciphertext in his encryption, it was sort of noisy. So every ciphertext, when you decrypted it, there was some probability of error. But fresh ciphertext, there's a notion of fresh ciphertext when you just encrypt it, where the error was really small. And then every time that you compute, now you take 2 encryptions, and you do some magic to get a new ciphertext whose corresponds to the adding those 2, or multiplying the plain text. It says every time you do an operation, you sort of add noise, because the noise that was in the original 2 either adds or multiplies. Very quickly, you get garbage. It's not true anymore that if you decrypt, you get the program evaluated on the original plain text. This is how do you get rid of this noise? So he said, you know what? The way that what I'm going to do, I'm going to have a routine called bootstrapping, which takes in a noisy ciphertext and replaces it by a new fresh ciphertext, CTA star. Both of them decrypt to A. But this guy has a lot less noise. And in a minute, we'll see how he does it. But he says, in that case, I can do operations, get too much noise, I bootstrap. I go back and have less noise. I do more operations, I bootstrap. But how do you get rid of noise? I mean, one way to get rid of noise is that you decrypt, you find what A is, and you re-encrypt, with a fresh ciphertext that has little noise. That you can't do, all right? The cloud is not supposed to be able to decrypt and get rid of noise, okay? And this is where the genial idea is. He said, well, what we're going to do is somehow we have this ciphertext, and I want to get rid of, and it's a noisy ciphertext. I want to get rid of noise. What I'm going to do, I can't decrypt, but I can homomorphically the decryption itself is an algorithm. Maybe I can run this decryption algorithm. Think of it as an homomorphic evaluation of the decryption algorithm. But that's very strange. If now the cloud can decrypt, it says, no, we're going to give the secret key encrypted and do a homomorphic evaluation of the ciphertext and the encryption of the secret key. So in some sense, I decrypt under the hood. So sort of I decrypt the message that has a lot of noise, but under sort of the umbrella of encryption, I throw away the noise and re-encrypt. Okay, so there was in my bad type, it was here. So what you're going to do is you're going to take a decryption algorithm, which takes an encryption and a secret key, but both in encrypted form, and you run an evaluation on it. What does evaluation do? It decrypts this guy. The pink means it's encrypted. It decrypts it, and now it has A in its hand, but it doesn't really have A in its hand. It says A is still in encrypted form. Now, though, you can sort of inject, have a fresh encryption of A with fresh noise, and that has lowered the noise. He was much better at breakfast than I am now at lunch, but he didn't have jet lag. Maybe he did, it was in Germany. In any case, this is magic, okay? Magic because I just said that by doing a lot of procedure computations, you inject more and more noise. So maybe also by doing this computation, you're injecting noise. So his magic was that he showed a scheme where decryption was very few operations. So the amount of noise that was introduced by doing the evaluation of decryption was so little that you can support it. This is, whoever's intrigued by it should read that paper, but otherwise we continue. So why is this relevant to me? Because what we're going to do is we're going to use that exact same bootstrapping mechanism which he had for reduced noise for getting deniability. Okay, but instead of, my issue is not noise. My issue is that going to enable me to somehow sample ciphertext, okay, without going through the encryption routine. Usually I'm supposed to take a 0 and encrypt it, take a 1 and encrypt it. Somehow, what bootstrapping is going to do for me is that I'll be able to just choose something at random in the big space, which I said usually decrypts to 0, okay, and run bootstrapping on it, which will replace it by a fresh ciphertext of 0. And now, this is a way to come up with things that look like legal ciphertext, okay, of 0s and 1s. Right? Take something at random at 0 and do a bootstrapping to it. And what does that mean have to do with deniability? Before I go into the nitty-gritty of it, the key idea is this. I want to be able to tell you that I didn't encrypt a 0. I encrypted a 1, or vice versa. If it's plausible that I didn't actually take randomness and encrypted a 0, I just chose a random, just a random value. I claim I did. How do you know I didn't? It's indistinguishable from going through the 0 and encrypting it. Okay? So that's a legitimate story. If that's the legal way to encrypt, which is just to take a random element in the codomain, okay, and then bootstrap, I don't know the randomness for it because I never took it. Okay, so that's kind of the crux of the idea there, is that there is a way to encrypt which is really, you can't tell whether I went through the legal procedure or I just chose something at random to encrypt a 0. And that will lead to a fully deniable method. So what time is it? Maybe I'll skip to the, how much more time do I have? 10 minutes, 15 minutes? 10 minutes, okay. So I'll just flash these, but essentially the way to encrypt then is, if I want to encrypt a bit B, I choose a whole bunch of X's which are 0s and 1, so that the exclusive OR of them is B, okay, B mod 2. Any bit I can break into a bunch of random bits such that XOR is the bit, right? So a bunch of 0s and 1s that XOR to a 0, that's how I break B, being equal to 0, or that exclusive OR to 1, B equal to 1, okay? And then the way I encrypt the XIs, the 0s, is I sample just at random, as I said. But the way that I encrypt 1s is that I actually choose from randomness and I go through the illegal encryption of a 1 with that randomness. And now the ciphertext that I send, and here's where compactness comes. So actually compactness also comes from the fact that fully homomorphic encryption is compact. Compactness is just the XOR of the bootstrap of all the ciphertext. In this case, this is a ciphertext, just random value. And in this case, this is the result ciphertext, the encryption of a 1. So when I do this operation, right, by the compactness of fully homomorphic encryption, I get a small outcome. Okay, but if you decrypt this, what does it decrypt to? It decrypts to whatever was meant by the encryption of R1, which is, let's say, maybe if it was a 0, or if it was a 1, so it's the XOR of the values of the XIs, which is the encryption of the bit. Okay, this is just like, seems overwork. Instead of just encrypting the bit directly, I break it down to a bunch of bits, I encrypt each one individually, one just by choosing at random, one by going, okay, for 0s, and okay. Now, why do I do that? By the way, so what's the randomness that I have to present to the guy with the hat when he comes and says, show me the randomness? It's these were randomly chosen, these XIs, and this was randomly chosen, and the little r were randomly chosen. So this is all the randomness I have to produce. How do I fake him out? How do I fake him out? So the idea of faking out is, here's a fake. So let's say again, I voted just for a bit for the sake of this talk, and I want to claim that I voted for the complement bit. And this is the randomness I really used. Okay? And now I want to produce new randomness, which will look just as good as this original randomness. He won't be able to tell them apart. How do I do that? Well, of course, if I don't want to fake him out, I don't have to do anything. But what if I do want to fake him out? So first of all, if I switch from, let's say, 0 to 1 or 1 to 0, all that means is that there's one of those bits of the x's which has to switch, right? So in fact, I am going to look for one of the bits that is 1. So remember, the xi's were such that if you, like the 0, 1, 1, 0, 1, which I XOR them together, I got the, when I sum mod to them, I got the b. So I choose one value, which was a 1, and in my mind, as a mental experiment, I flip it into a 0. Okay, so now if I XOR those things, I get exactly a complement vote, right? And now I need to produce randomness. All the randomness is unchanged, except the randomness that was associated with this location. It used to be an encryption of 1, okay? And which meant that there was a little r, and I really encrypted the 1 properly when I sent it to the government. But what I'm just going to pretend that actually that's not what I did. That actually this was just something it was the encryption of 0, so I just chose it in the random codomain of ciphertext. And that's it. Notice that the ciphertext remains unchanged. Why is it? Because remember, the ciphertext that we use, we took this bootstrapping of all these big R's. So if it was just random, I did bootstrapping of the big random guy that took from the ciphertext size. And if it was encryption of a 1, I also took the big R. So I'm still doing the same operations exactly on the same big R's. It's just that in my mind, I'm saying one time the R was just chosen at random, one time was really the encryption of a 1. So the ciphertext remains the same. And the key is now that the randomness, all that's changed is one xi switched from 1 to 0, okay? And one big R I claimed was a big R and I gave that rather than the little randomness. Anyway, the point is that this works. It's compact, and I want to go forward, unless there's a question. This is very technical, and probably is best for people who read the paper, and maybe they forgot, and now. Any question? Okay, so let's go forward, online, offline. The new landscape is that this is where we're at. 2017 is actually right now. This is the scheme. I want to just say something about quantum, okay? So what does quantum have to do with anything? So these days, people are working on quantum computing. They're discovering there's a lot of things you can do with quantum computers, which we could have done before, but now you could do it for quantum circuits. So in other words, homomorphic encryption, we know how to do it for classically. There's results of Urmila Madeev, who's now in Caltech. She was a graduate student at Berkeley, of Umesh Vazirani. She showed how you could do homomorphic encryption for quantum circuits. Or verifying computation classically, now they know how to verify quantum computation with a classical verifier. But there are some results which show that you can use quantum computers to do more than you can do classically. And this is going to be one of them. So we'll show how to do deniable quantum encryption, where you get negligible deniability, compact, zero decryption error, and prevent coercion before the fact, something that classically, provably, you cannot do. What's the idea? We still have the government. But now, in this futuristic world, and again, you know, I really, I always get somebody in the audience, so I warn you not to ask me. They say, but everybody's going to have a quantum computer. You know, I don't know. Maybe they won't. The idea is the principle, okay? So it's a beautiful idea, and I can show that it's related to other things. So in this futuristic, unbelievable, you know, what was it, the movie that we were always seeing, 2001, with the Space Odyssey, right? Okay. It doesn't seem that futuristic at all. You're talking to the computer, it's destroying the world, you know. This is kind of a current problem or problem to come. Everybody has a quantum computer, okay? They have a quantum laptop. What does this laptop do? It does something, okay? When it wants to vote, it comes up with a classical encryption of a vote and sends to the government. And the government still tallies the votes, okay? But what does this help me with? Now he comes along and says, show me that you voted for me. And I am going to, and the advantage of going quantum is the following, is that there's these beautiful results by Umesh and Vidik and a whole bunch of other people, which show that you can produce randomness internally in a using quantum entanglement and measurements, okay? So randomness is no longer going to be provided by the sender. It's actually produced by the machines, and I have no control over it. So there, in some sense, it makes no sense that I will show you the randomness because I don't even know what the randomness is. It's produced by the machine, 1. two, so what's the deniability analog? Okay, what does it mean then that if somebody comes and says to me, prove to me that you voted for me? What is the analog in a quantum? The analog is that maybe you give him access to all your quantum states and let him look at it. Now, it's well known that if you never measured any of these quantum states, he can reverse and find out what you voted for. But it's also true that if he sent out a ciphertext, okay, he must have done, corresponding to a single bit, he must have measured a single bit at least, otherwise he couldn't get a classical output. So we're saying, if you only allow this guy here to do one single bit of measurement, and then when the hat person comes and examines your computer, we prove that by looking at the states, the quantum states, you cannot tell apart whether they encrypted at 0 or encrypted at 1. There's exponentially small probability of distinguishing if you look at the quantum states, okay? So, okay. So this is what I mean. 1, the randomness is produced internally. 2, you let the coercer examine your quantum states, and then you prove that he cannot tell from the contents of your computer whether you encrypted as 0 or 1. So again, it's deniable in the sense that there's no point in coercing, because he cannot tell them apart. The magic here is that really the magic is that you can prove that he cannot even coerce you before the fact. So even if he tells you what to do, he cannot force you to do one thing or another because you don't have results yourself. It's the randomness, the internal measurements, entanglement, and computation that you're doing are going to be such that you don't have full control over them, and therefore he cannot tell you what to do, okay? And yet you will encrypt either a 0 or 1 as you intended. It will decrypt it properly on the other side, and you can deny it. So just quick, this is the result. Under LWE quantum polynomial hardness, you can get compactness, perfect decryption, negligible detection probability, deniable encryption scheme. And I don't know, those of you who have done some quantum computation, so again, it's a subset. You know, there is this beautiful idea by Urmila where she said that there's this thing called claw-free trapdoor functions, where these functions where there is a y here, and there are 2 inverses. And claw-free means that it's hard computationally to get more than 1 inverse, but there are 2 inverses. And this is something we use in cryptography from the 80s for digital signatures. But what Urmila noticed is that you can build something like this based on this learning with errors in quantum world, okay? And she noticed that this enables you to do magical things, okay? And the one magical thing is, the main one, is that you can encrypt in a way, kind of, this is her idea, is that in a quantum world, in a classical world, I was going to say real world, in a classical world, you take an x, compute f4, this is a one-way function, and now you have 1 inverse, but you don't know how to get the other inverse. In a quantum world, there is an ability to sample y such that you're holding both inverses in a superposition. But you can't figure out neither x0 or x1, because as soon as you're trying to figure out your measure to try to find, it collapses and you only find 1. And moreover, what she really showed, which was interesting, was that you can come up with y and some sort of random bit whose result is this, a d, which you can figure out, times the XOR of x0 and x1. This doesn't mean that you know either x0 or x1. You know the XOR of them. And this is a pseudorandom bit. And that enabled her then to talk about a new type of encryption, which is essentially using this as a one-time pad to encrypt your message bit. Okay? It's this magic that also is going to lead to deniability, because what we can prove is essentially this method is also deniable. Again, you have to talk about looking at the contents of your registers and show that you cannot tell apart whether the outcome of this bit is a 0 or 1. Yet, on the other side, the decryptor, he has a trapdoor. So he knows, so this function has a trapdoor. So he's able to compute both x0 and x1. So when he gets this encryption, he gets a z, and M XORed with B, he can figure out what B is, because he can figure out both pre-images, x0 and x1, figure this out. This was given to him, and he can decrypt. All right. I think that's it. You can coerce before the fact. I won't get into it, because I know I'm out of time and out of patience. There was was a third part. I will not talk about it, but I just want to go fast forward ahead to say my conclusion. Sorry, how do you point to the end? I'm almost there. There I am. That's, no, one before. So the conclusion is deniability, in my opinion, may be the ultimate extension to the right to be left alone. People here right in the beginning raised the question, is it reasonable to be able to deny everything? You know, I can deny everything now. I went into the booth and I could deny it. I'm doing some computation on my computer and I unplug it from the internet. I deny it, you know. Why is it that with the use of technology, I should all of a sudden, it's not okay to deny? It's unclear. That's one response. And the other response is that maybe you are able to deny and also have a special mode where you cannot deny because the secret key is being held by someone and then they can really decrypt what you intended to do. Thank you. I just want to say one thing that I think that I didn't say, and that is about the quantum. That what's interesting about it is that we are looking more and more now for some evidence that quantum computers can do more than classical computers, or that quantum supremacy. And you all know about the Google experiment, and now there's a bunch of results saying that they can do it classically as well. And another thing you can ask is, can you really prove that your computer did more than classical? In some sense, this result is hinting in the direction is yes, because you can do this, you can show that you cannot coerce before the fact classically, but you can do, sorry, the other way. You can coerce before the fact classically, but you can't do it quantumly. So any type of result that indicates that there is superiority, at least in principle, to a quantum computer, provably so. Because with factoring, probably you can factor classically as well. I mean, right now we have a quantum algorithm for factoring. But to have, in principle, a proof that something is possible quantumly, it cannot be done classically, is very interesting. Both as a motivation to show that quantum exists, and maybe as evidence that it doesn't exist. I mean, we don't know the rules of quantum mechanics hold. We kind of assume they do. Yeah. Yeah.
But it can still be off with positive probability. And so the ones that are possibly losing sight always say that the randomness was such. Would you agree that the randomness was such that this is the correct person that is affected?
That's a great question, and it really it touches another topic. So there was a census in the United States about 2 years ago. Would use methods called differential privacy. Differential privacy methods are where you don't actually, in some sense, don't answer correctly, the questions of the census, but you put some noise in your answers. And then they tally up these answers, and then on the aggregate, you're saying that you get a good outcome. And now there are court cases where certain districts that were going to get less resources because of the results of the census, they say, but there was some probability, because you insert noise, that the results of the census are incorrect. And my constitutional right has been violated. So this is the same question. It's like saying an opposite party says that the election has been stolen because there was a probability of error. Good point. In some sense, it leads to this other question. It is, if we're going into a world where everything is going to be based on digital stuff and maybe big data and so forth, and eventually we're going to get court cases where people are going to say malpractice. Or some other, and they say because this was a statistical model and there's some probability of error, and you caused this harm to me. So I think courts are going to have an understanding of statistics and an acceptance of statistics in order to be able to rule on these type of things, similarly in the election case.
But here is a possible alternative, which I don't know whether one might not be able to get positive results on that. But one could say that there is some noise, but then when you see that the separation is large, you know that the answer is correct. In the sense the noise is limited to a certain ball. If it were this, there is no good one,
That's true, but that acts against deniability. Because if the separation is large, then maybe also the guy with the hat can tell apart whether you encrypted using the randomness you give is R versus R prime. That's the tension there.
Yeah.
But the fact that there's a tension doesn't mean that there isn't a solution. But right now, I don't know. Any other questions? Hi, yeah. The cursor, yeah.
Ask him to use my key. And
Yes.
then after you give the vote, prove to me that, indeed your vote
Yes,
is
so
correct.
so this is coercion prior, right? Before the fact. So he forces you to use the randomness, you're saying, or to use
Right,
something?
right, right.
Yes, it's possible classically, and you can prove that it has to be possible, but quantumly it's not possible. So that's the big thing about the quantum, is you can prove that he can, even if he coerces you before the fact, there's nothing you can still deny. So there's no way to, in some sense, prove that you did one thing versus the other. So it doesn't matter what he says, you cannot prove, what you essentially show is that you cannot both produce a ciphertext and maintain enough state so that you could verify.
Okay.
Yeah.
My question is more from the computing standpoint. So for some of these techniques to become commonplace for people to use, the cost of, for example, bootstrapping today is substantial, and just the fully homomorphic encryption strategies are, orders of magnitude slow. Are there algorithmically people have been looking at, I know that hardware people have been trying to reduce the cost, but are also algorithmically also looking at reducing the complexity or reducing some of the costs? That
Yeah, absolutely. I mean, people in this field are very aware of the fact that bootstrapping is expensive. So it's ongoing work, both in academia and in industry, to reduce the cost of bootstrapping. Part of it might be because you are going to pack more plain text into ciphertext. You can do computing in parallel in a way that the error doesn't, that the depth of the circuit doesn't, it sort of remains shallow rather than increase, which means that you're going to need to do bootstrapping less often. Yeah. Yeah.
Do you hope we can achieve deniability using additive only of encryption?
Using what?
Additive only.
Additive only. Yeah, I don't see how to do it. I need bootstrapping in order to prove the results. But if you think about it, bootstrapping was sort of secondary. It was in order to have everything look the same for the evaluation circuit. It was really the summing mod 2 that was key kind of to the functionality of it. Yeah. Yeah.
So there's this notion of opacity where both the secret and non-secret states produce the same output with some given inputs. So do you think there's a relation between the deniability and opacity? Because here also two different states with two different randomness produce the same ciphertext.
Okay, so opacity is again what?
So in opacity, basically you have a secret state and a non-secret state, and you execute your program from these two initial states.
Yeah.
And you get the same output.
Yeah.
So if someone is looking at the output, he or she will not be able to determine whether the starting point was a secret point or a non-secret point.
Yeah, absolutely. Sounds very similar. Except in your case, you know from the beginning, I guess, that you are that you want to deny. Is that correct? So you have a secret state and non-secret state, and
yes,
you have two types of computations. One is from the secret, from one of the non-secret, so that they end up in the same place.
Correct. So basically,
whereas here you are, if I claim, so the question is what the secret is in your mind. Is it the randomness or is it the vote? So if it's the vote, starting from the vote and doing it's the same computation to get to the end. I'm guessing that in your case you have two types of computing, one on the secret and one on the non-secret. But I'm not sure I understand your question. Maybe we can talk about it afterwards.
Oh, sure.
Yeah. Sounds related. Okay, thank you very much.
I request Professor Narhari to thank our speaker with a token of our appreciation.
I want to read it out. Let me read out what is there in this memento. Department of Computer Science and Automation, Indian Institute of Science, presented to Professor Shafi Goldwasser for her wonderful talk under the Infosys Science Foundation lecture, January 6, 2023. It's a great pleasure to present this memento to you.
Thank you so much. So beautiful. Look at that. It's like coercing before the fact. How did you know it was going to be a wonderful talk? But thank you.